Welcome to the deep dive. Today we're diving deep into chemical equilibrium. Um, that state where reactions seem to just pause? But it's really more like a busy city. Everyone's moving around, but the population is staying steady because people are always coming and going at the same rate.
That's a great analogy.
Thanks.
It is a dynamic state, not a static one. And it's everywhere, from water evaporating to those reactions that produce ammonia for fertilizer.
Yeah, okay. So before we get into all the details of the reactions themselves, can we start with something everyone can relate to? Like those soda bottles that go flat. You open one and the fizz is gone. That's equilibrium, right?
Absolutely. That fizz you're talking about is carbon dioxide that's dissolved in the liquid and under high pressure. But when that bottle's open, the pressure drops, so all that CO2, well, it rushes out, trying to reach a new equilibrium at that lower pressure. So, yeah, flat soda.
So those little CO2 molecules are just waiting for their chance to escape, and then boom, open bottle, freedom. But what's interesting is that it finds a new balance eventually.
Exactly. And the same thing happens with evaporation. Think about a glass of water left out. It slowly disappears because those water molecules are constantly escaping into the air. But if it were in like a closed container, they'd eventually hit that equilibrium vapor pressure where evaporation and condensation happen at the same rate.
Oh, so like a constant battle between the liquid and the vapor, trying to find that happy medium.
Precisely. Now imagine something a little more visual, like solid iodine. You leave those dark crystals in a closed container and you start to see this beautiful violet vapor. That color stops getting more intense eventually because the sublimation, the solid turning into gas, and deposition, the gas turning back into solid, they're happening at the same rate.
Oh, wow. It's like that dynamic city again, with the molecules moving between solid and gas, but keeping the population steady in each.
Exactly right. And scientists actually used radioactive isotopes to prove this was happening. Imagine adding a bit of radioactive sugar to, let's say, a saturated sugar solution. Over time, you'd find radioactivity in both the solution and the sugar crystals.
Wow, so even though it looks like nothing's happening, those sugar crystals are constantly changing.
It is, and it just goes to show that this dynamic equilibrium, it only happens in closed systems. In an open system, well, things can escape, so you can't get that true equilibrium.
Makes sense. So, okay, we've looked at equilibrium in these physical processes, but what about chemical reactions? Do they hit a similar balance?
Absolutely. Let's look at the Heber process. It's how we make ammonia. You mix nitrogen and hydrogen gas in a closed container, and they react to make ammonia. And if you could keep track of what's going on, you'd see the reactants decreasing, the product increasing, but then everything levels off.
So it's like it hits a wall and just gives up.
Not quite. It's reached a dynamic equilibrium where the forward reaction, making the ammonia, and the reverse reaction, where the ammonia breaks back down, are happening at the same rate.
So it's like a two-way street with molecules jumping back and forth, but it stays balanced between those reactants and products.
Exactly. And to prove this, scientists, well, they did something clever. They swapped regular hydrogen with its heavier isotope, deuterium. And they found all these mixed ammonia molecules in there, NH3, NH2D, you get the idea. It showed that the hydrogen and deuterium were moving around even at equilibrium.
Wow, so even at equilibrium, the molecules are constantly reacting? How do we measure this balance? I mean, can we tell how much a reaction goes towards equilibrium?
Yes, we can. It's called the equilibrium constant, Kb. It compares the concentrations of the products and reactants at equilibrium and factors in the stoichiometry of the reaction.
So if Kbat is big, that means more products, and if it's small, more reactants, right?
Yes, that's right. A large Kbase, let's say bigger than a 103, tells us the reaction goes almost all the way, mostly products at equilibrium. And a small Kbec, less than 10 to 3, that means the reaction barely starts and favors the reactants.
Okay, so Kbat shows who's winning that tug of war. What if we reverse the reaction? Does Kbat change then?
Yes, it does. You just take the reciprocal of the forward reaction's Kc. For example, if the Kc is 50 for the forward reaction, it's going to be 150, or 0.02, for the reverse reaction.
Oh, that's pretty cool. But what if we have reactions with gases? Don't we have to think about the pressure they make?
You're absolutely right. For gas phase reactions, we usually use Kt, which uses partial pressures instead of concentrations.
Kp, Kc, are they related?
They are. We use the ideal gas law to connect them. The relationship is Kp equal Kzrt, wherein is the change in the number of moles of gas between reactants and products.
So we have to watch out for those gases and how their numbers change.
Precisely. Now, it gets a bit more interesting when we have different phases in a reaction, like our iodine example with the solid and the vapor. This is called heterogeneous equilibrium.
Heterogeneous. Sounds complicated. Do we still use Kc or Kp for that?
We do, but there's something to remember. We only include the concentrations or partial pressures for things in the gas or aqueous phase in the expression.
Wait, we just ignore the solids and pure liquids. Why is that?
Their concentrations stay pretty much constant during the reaction. Think about a big block of ice and a little ice cube. They both melt at 0 degrees Celsius. The amount of solid doesn't change the melting point. It's the same idea here. The amount of pure solid or liquid doesn't affect the equilibrium.
Okay, so solids and pure liquids are there, but they don't really impact the equilibrium like gases or dissolved species.
Exactly. Now, before we move on to what can change this equilibrium position, let's talk about the reaction quotient, QC. It's like Kc, but we calculate it using concentrations at any point in the reaction, not just at equilibrium.
So QC is like a snapshot, and Kc is the destination.
Exactly. By comparing QC to Kc, we can predict which way the reaction needs to go to reach equilibrium. If QC is less than Kc, it needs to make more products. If QC is more than Kc, it goes back towards the reactants.
So it's like a compass pointing the reaction in the right direction to find that balance.
Exactly. It's a really useful tool for understanding how reactions work even before they get to equilibrium.
Welcome back to the deep dive.
We were just getting to how we can actually change these equilibria, and temperature is a big one.
Okay, so we can heat things up or cool them down to push reactions in one direction or another. How do we know which way they'll go, though?
That's where enthalpy change, or AH, comes in. Remember, it tells us if a reaction is exothermic, so giving off heat, or endothermic, taking in heat. We can think about heat as like a reactant or a product in the reaction.
So if it's exothermic, heat is a product, and adding more heat would push the reaction back towards the reactants. Kind of like if you cram more people into a room, they're going to want some space.
Exactly. Le Chatelier's principle, the system tries to get rid of that stress. Increasing the temperature of an exothermic reaction helps the reverse reaction, and K-near actually goes down.
Oh, so turning up the heat makes the reaction less likely to go forward. Okay, I guess that's equilibrium. What about endothermic reactions then?
Well, for those, heat is a reactant. Adding heat gives the reaction a boost, pushes it towards products.
So it's like adding fuel to a fire.
Exactly. And because of that, Kc for an endothermic reaction goes up as temperature increases.
Okay, so heat is kind of controlling the equilibrium. Are there any good examples of this?
Sure, like the dimerization of nitrogen dioxide. 2 NO2 molecules combine to make N2O4. It's exothermic. So if we had a test tube of brown NO2 gas and cooled it down, that color would fade as the equilibrium shifts to the colorless N2O4.
So we could actually see the equilibrium changing, and if we heated it up, the color would get darker because of more NO2.
Exactly. It really shows how temperature changes what's in the equilibrium mixture.
Okay, temperature makes sense. What about pressure? Does that change the equilibrium?
It does, but it mainly affects reactions with gases, and only when the number of moles of gas is different for reactants and products. Think about the Haber process again. We've got 4 moles of gas on the reactant side and only 2 on the product side.
So if we squeeze the system up the pressure, it wants more space, so it shifts to the side with less gas molecules.
Exactly. Increasing the pressure makes the forward reaction go faster. More ammonia, less total gas molecules to lower the pressure.
Like making the molecules huddle up for space. And if we lower the pressure, they want to spread out, so that favors the reverse reaction.
Yeah, you got it. But remember, if there's the same number of gas moles on both sides, changing the pressure won't do anything to the equilibrium.
Gotcha. So pressure's got its limits. What happens if we add like an inert gas? Does that change things?
Good question. An inert gas, something like argon, it won't react. If we add it at a constant volume, the total pressure increases, but the partial pressures of the reactants and products stay the same.
Partial pressure, so each gas is only making part of the total pressure. So if those don't change, the equilibrium's fine.
Exactly. It's like a sneaky trick. The total pressure changes, but not the individual ones that the equilibrium actually cares about.
Okay, so we've talked about concentration, temperature, and pressure. But what about catalysts? Don't they just make things go faster?
That's right. Catalysts give a different way for the reaction to happen. They lower the activation energy. But the important thing is they make both the forward and reverse reactions go faster by the same amount.
So it's like a boost for both sides. But if they both speed up, doesn't that mean the equilibrium doesn't move?
Exactly. Catalysts don't change Kc or what's in the mixture at equilibrium. They just help it get there faster.
Like a faster delivery service, same destination.
That's a great way to think about it.
So it's all starting to come together now. We've seen how we can change things up by tweaking the conditions. Are we ready to get into ions and solutions?
Yes, definitely. Let's see how all this applies to ionic equilibrium.
Welcome back to the deep dive. Last time, we talked about how temperature, pressure, even catalysts can change that balance of chemical equilibrium. Now we're getting into ionic equilibrium, where it's all about charged particles.
Exactly. All those equilibrium principles we've talked about, they're still true here, but with a little twist. Now we're looking at ions in solution, those charged atoms and molecules that make solutions conduct electricity.
Right. Like those electrolytes they talk about in sports drinks. Those are all about ions, right?
Absolutely. And all those ions are constantly moving around, forming and breaking bonds, trying to reach equilibrium. But before we get too deep into that, let's just go back to basics for a second. Acids, bases, and salts.
Okay, so acids are sour, bases are bitter, and salts are, well, salty. But I'm guessing there's more to it than that.
Definitely. In ionic equilibrium, acids donate protons, those positively charged hydrogen ions, H+, to water molecules.
Acids are proton donors. Got it. And what happens to those protons? They're not just floating around, are they?
No, they're not. They attach to water molecules, making hydronium ions, H3O plus taxi. It's like the proton hitches a ride.
Oh, like a proton taxi. Okay, so what about bases then? What do they do?
Bases are proton acceptors. They grab onto those protons and often make hydroxide ions, OH, in the process.
Okay, so acids donate, bases accept. It's all about those protons.
Yeah.
So where do salts fit into all of this?
Salts are what you get from acid-base reactions, like table salt, sodium chloride. You get that when hydrochloric acid, a strong acid, reacts with sodium hydroxide, a strong base.
So salts are like the outcome of the reaction.
Yeah, you could say that. And when salts dissolve in water, they break apart, releasing their ions back into the solution.
Okay, so we've got these acids donating protons, bases accepting them, and salts breaking apart. So how do we measure how strong these acids and bases are?
That's where ionization constants come in. Ka for acids and Chi for bases. They tell us how easily they ionize, how willing they are to give or take those protons.
So a strong acid would have a large Chi, meaning it's ready to give up its protons, right?
Yeah.
And a weak acid holds on tighter, so a smaller Ka.
Exactly. Strong acids like hydrochloric acid, they pretty much completely ionize in water, so they have very big K values. Weak acids like acetic acid, the one in vinegar, only ionize a little bit, so their Ka values are smaller.
Ka is like a measure of how generous the acid is with its protons. And Kb for bases, same idea, but the other way around.
It is. The larger the Kb, the stronger the base, the more it wants those protons.
Okay, makes sense. But what about water itself? Is it just there watching all this proton trading happen?
Water is actually pretty interesting. It can act as both a weak acid and a weak base. It's called autoimmunization. Water molecules react with each other. One donates a proton, the other accepts it, and you get those hydronium and hydroxide ions.
Wait, so even pure water isn't really neutral?
It is. This autoionization has its own equilibrium constant, Kw, called the ionic product of water. At 298 K, it's 1 by 1014, which shows that balance between the hydronium and hydroxide ions.
So even pure water has a tiny bit of acid and base in it. How do we measure how acidic or basic a solution is?
We use the pH scale, which is the negative logarithm of the hydrogen ion concentration. It's a way to express those tiny concentrations more easily.
Logarithm, those bring back memories. But so a low pH is acidic, high pH is basic, right?
Exactly. Less than 7 is acidic, greater than 7 is basic, and 7 is neutral, like pure water.
Okay, I remember that. How do we actually measure the pH?
We can use pH meters. They use electrodes to measure the potential difference, which tells us the hydrogen ion concentration.
That sounds complicated. Is there a simpler way to check?
Yeah, we have indicators. They change color depending on the pH. Like litmus paper, it's red in acid and blue in base. Each indicator changes color at a specific pH range.
Like a color-coded pH chart? Cool. We've covered acids, bases, and pH, but what about those salts? Do they just hang out, or can they change the pH too?
They can definitely change things. It's called hydrolysis, where the ions from the salt react with the water, and that changes the balance of hydronium and hydroxide ions.
So salts can make things more acidic or basic. How does that work?
Let's say we dissolve sodium acetate. That's the salt from a weak acid and a strong base in water. The sodium ions don't do much, but the acetate ions from the weak acid, they react with water, grabbing protons and making hydroxide ions.
So they're making the solution more basic.
Exactly. And the opposite happens with a salt like ammonium chloride, from a strong acid and a weak base. The ammonium ions give protons to the water, So you get more hydronium, and the solution becomes acidic.
So it all depends on where those salt ions came from, weak acid or weak base, to know whether they'll make the solution more acidic or basic.
You got it. And if the salt is made from a strong acid and a strong base, the solution will be neutral. Like everything's balanced.
This is also interesting. What about solubility? We mentioned sparingly soluble salts earlier. How does that fit into this?
It's all connected. Let's think about silver chloride. That's a sparingly soluble salt. Only a tiny bit dissolves in water, and you get silver ions and chloride ions. This has its own equilibrium constant, KSP, the solubility product constant.
So KSP tells us how much of that salt will dissolve in the water.
Exactly. A smaller KSP means it's less soluble. The ions prefer to stick together in the solid instead of dissolving.
So it's like a measure of how much those ions want to stay together. Can we change the solubility?
Yes. We can use something called the common ion effect. Imagine we have a saturated solution of silver chloride, so it's got as much dissolved as it can hold. Then we add sodium chloride, which puts in a bunch more chloride ions.
So there's suddenly a lot more chloride ions. What happens then?
Le Chatelier's principle comes in again. With all those extra chloride ions, the system wants to get rid of that stress. It pushes the equilibrium back towards solid silver chloride, making it less soluble.
So by adding that common ion, we're pushing the silver and chloride ions back together.
Exactly. And that's just one way we can use equilibrium principles to change solubility. This has been an amazing look at ionic equilibrium. We've learned about acids, bases, salts, what pH is, and how those salts can change a solution's acidity or basicity.
Yeah, it really shows how dynamic these chemical systems are, always trying to find that balance, even if it means changing and adapting to different conditions. It's like a constant dance with those ions swirling around, always trying to find that equilibrium.
Absolutely. And as you keep exploring chemistry, remember, equilibrium isn't about staying still. It's about change, adapting, and balancing those opposing forces. Thanks for joining me on this deep dive into ionic equilibrium.
My pleasure. Until next time.